પેલું વર્ચ્યુઅલ લેબ એમાં ચાલતું જ નથી સિમ્યુલેટર. Very good morning, students. So today, right now, we have a lab, and last two lectures we have a lecture. So what I think today we'll do the lab, but not first two lectures, but we'll do it in the last two lectures, because to study in the last two lectures is very difficult. So what I think, we take first two slot as a lectures, and last two slot as a lab. Today we'll do the lab of second experiment. And so right now we consider a two slot of lecture, and then last two slot as a lab considered, and today we'll do the experiment. And so first let's do, you are on fresh mind, so we can concentrate on lecture. Due to that reason, we first consider it, then we'll consider a lab today. We'll do the lab today. We'll do the second experiment. Then so last lecture we calculate the example of equal size of CSTR in series, and we calculate 2 to 3 gate examples regarding this. And now we go for the unequal size of CSTR in series, and there are two objectives. The first objective is to how to calculate the concentration and conversion after the last MFR or CSTR, and second one, which arrangement system I use, so that within the minimum amount of volume we get a maximum amount of conversion. So that is the two objective. But the first we'll consider the how can I find out the concentration and conversion after the second or last CSTR. The first topic will study the finding the conversion in a given systems. First we'll do the topic will be the finding in a given system. So we find out the equations in equal size of CSTR in series, but there is no any particular equation here for finding out the conversion and concentration in unequal size of CSTR. There is no particular equations we have to be there, but we have to use the graphical technique. What we have to do? We have to do the graphical technique to find the conversion in a given systems, whether the small one is first or whether the large is first. But so we'll use the graphical procedure. So how we'll do the graphical procedure? For examples, we consider the 3 MFR in series. Consider, for example, we consider three MFR or CSTR, both same name, in series. And all three are maybe a different, all are in different size. They are not the same size. So we can write down the equation like this also. Tau is equal to actually like tau divided by C0. Performance equation of the one reactor is MFR. Performance equation is tau divided by C0, space time divided by initial concentration, is equal to, I write down the equation in terms of concentration, not conversion. So here above one the conversion will be there. So uh, convert conversion into the concentration. So C0 minus C1 divided by C0 multiply by R1. C0 C0 cancel out. So I get one equation, tau is equal to C0 minus C1 divided by minus R1. And we'll consider here tau 1. Our ultimate goal is to find out the concentration after the last CSTR, once we arrange CSTR and series, any reactor concentration we can find out using this. For example, let's do the reverse of this one. So 1 divided by tau 1 is equal to minus R of 1. Here I change one, not C1 divided C0 minus C1, but it's C1 divided by C0. So here minus sign will be considered minus sign here. Okay? So for any of the reactor, this is for any reactor, for example, for ith reactor, we can generally write it down minus 1 divided by tau I is equal to minus R of I divided by Ci minus Ci minus. That is the general equation. So what we have, how can we find out the concentration? We have to draw a graph. The graph is between rate of reaction versus concentration. So we have to construct a plot. Of minus R versus concentration. For we have to construct minus R versus concentration. It means we have to draw a graph, rate of reactions versus concentration. So let me draw a graph of rate of reaction versus concentration. So we have to draw a graph minus R versus concentration. Okay. So we have a certain data or general curves are there for the systems for rate versus concentration. So generally first we have to after doing this, some experiments, we have a general find out the data for rate versus concentration. Now what we'll do, we can find out the we know the value of the uh, initial, we know the initial value of the concentration. So we have to mark the point here, C0. First, we have a, after doing the experiment, we have a data, or general data regarding the rate of reactions versus concentration. Here we can predict the concentration, nearly we can predict the concentration. And it's a one method to find out the how can find out the concentration after the any reactor. So we know generally what is the initial concentration we feed into the reactor. Now here the equations we have one above equation, 1 divided by tau I minus 1 divided by tau I is equal to minus r of I, r of 1 divided by, for example here, C1 minus C0. So it's a here one type of slope. For examples, slope r of 1. So it's 1 is 0 minus 1 rate of reactions. Here C1 minus C0. So two concentration and one reference concentration of rate equation. So it's a one type of slope we will consider this one. Here it's a one type of slope. It's C1 initially no concentration. At C0 initial concentration we consider as a reference, and at C1 there is one rate of reactions. So we can mark the point rate of reaction for concentration. But before doing it, we can know the space time, because once we have a reactor, whatever the reactor we have, we know the volume, and we know the how amount of volumetric fluid we feed into it. So what will be there? So we can consider, we can find out the space time for this reactor, and the after finding out space time, we have to do 1 divided by tau, and whatever the value we have to convert into the slope. So after slope, we can find out with one angle. So once we do the find out the slope and we convert into the angle, we can get this type of things are there. So if you are measuring it, so it's here is a one type of slope, and slope value we are getting is equal to minus 1 divided by tau, 1 for one reactor, and it's ultimately it's a value of minus r of 1 divided by C1 minus C0. And if I make the line here, then whatever the concentration I here one, that will be the concentration after the first reactor. So here initially C0, here initially C1. So we can predict the value of concentration one after the one reactor. Now if we have another reactor, that is the inlet of the inlet of the first reactor, and if you want to find out the second, so if one this one is a volume and volumetric flow rate is somewhat different than the first one, then we have to find out tau 1, tau 2, then we have to do 1 divided by tau 2, we have to convert into the slope, and with we are getting 10 inverse the value, and then we are getting the slope with one angle, and that we have to do it from here, and here it's a value of minus r1. Here it's my value of r2. Second reactor, first reactor, because in CSTR we have only one r1, and then we have to mark this point here, and whatever the concentration we are getting, that concentration will be the after the first reactor. Same if we have another reactor in series, then again we have to find out the space time. We have to do 1 divided by space time, and we have to mark point here. We have to draw a slope, and we have to mark that here, and we did 3. Then so each and every time we can find out the concentration, and once we have a concentration, we can find out the conversion term. So by this way, we can also find out the concentration and conversion using this graph. Let me show if we have any example or not. So this is the procedure to find out the concentration. Just 1 minute. I would like to show if we have any example regarding this or not. we do not have a same examples like construction R versus C, but we have one example in that two CST are having a different size, and once they are in different size, how to calculate the concentration. We don't have any example regarding graphical, but general example, two unequal size of CST we have. So let's calculate that example. So one example is see in your screen. We have to use the same equation like tau is equal to concentration difference divided by rate equation divided by rate of reaction. So as you see in your screen, there is a example. It's a combination of two example. Like a there are two example in one question. So what is the example? The example is a liquid phase reaction A gives B conducted in isothermal CHTR having residence time of 2 seconds. Space time or residence time, it's the same. So they are using the different word. Residence time is 2 seconds. So we are here, we can consider tau having 2 seconds. The inlet concentration of the species A is 2 moles per liter. Initially, Ca0 is equal to 2 moles per liter. Outlet concentration is 1 mole per liter. So Ca is equal to 1 mole per liter. It means conversion from Ca0 minus Ca divided by Ca0. So rate law equation minus Ra is given, small k multiplied by Ca divided by capital K plus Ca, where small k is equal to pi mole per liter divided by second. So this is the small k values. The first they ask is to calculate capital K. They ask is to calculate capital K is in mole per liter. And so we have an equation. This is the equation we'll use this one. Tau 1 is equal to C0 minus C1 divided by minus Rho of 1. We'll use this equation. Tau 1 is equal to C0 minus C1 divided by minus R of 1. So tau 1 is equal to C0 minus C1 divided by minus R of 1. So here we can write down Ca0 minus Ca1 divided by tau 1. So tau 1 we have a value of tau 1, that is the 2 second. Ca0 we have Ca0, how much we have? It's a 2 mole per liter. So 2 minus Ca1 is 1 minus Ra is equal to small k, it means 5 multiplied by Ca1 1 divided by capital K plus 1. Ca it means final concentration. Ca it means final concentration. So once we calculate it, can you tell me the answer? What will be the answer for big K? Can you tell me the answer of capital K? Students, can you give me the answer of capital K? So here it's a 2 is equal to 2 multiplied by capital K plus 1 is equal to 1 divided by 5. So sorry, we can write down like this also. So 2 is equal to 1 multiplied by capital K plus 1 divided by 5. 10 is equal to capital K plus 1. So capital K is equal to 9. So any option having 9? Yes, we have B option 9. 9 moles per liter. Yeah. So capital K is equal to 9 moles per liter. Now they are asked another question. If same reaction is conducted in series of 2 CSTR with residence time 1 second and 0.2 second. So this residence time 1 second and 0.2 second, it's give the information regarding these two CSTR are not having the same size. They are having a different size. Due to that reason, they both have a different residence time. Inlet concentration of A in moles per liter required to attain an outlet concentration of A 1 mole per liter. It means that you have to find out the initial concentration of A whenever we are entering a reactor. At the time Ca is given, final is given 1 mole per liter. But how much we are introducing here, that we have to find out. Here tau 1 is given 1 second. Here tau 2 is given 0.2 second. It means both having a different volume. So let's find out the Ca0 initial concentration required to attain outlet concentration. So then inlet concentration of A moles per liter. So we have to find it out. We'll use the same equation, and we have rate equation values also we have. So just put down the things in equation, and then we can easily find it out. Okay, so let's find it out. So what are the data we have? The data we have tau 1 and tau. So we have a Ca2. We have Ca2 is 1 mole per liter. Tau 1 is 1 second. Tau 2 is 0.2 second. Yeah? And minus R is equal to, we have K multiplied by Ca divided by capital K plus Ca. Small k divided by Ca multiplied by plus capital K Ca. So now we use this one. So how we can use this one? Tau 1 is equal to Ca0 minus Ca1 divided by R1. It means small k Ca1 divided by capital K plus Ca1. Huh? Okay. So tau 1 value we have, it's a 1 second. Now Ca0 we don't have. Ca1 we don't have. So Ca0 and Ca1 we don't have. So we cannot use the first one because outlet concentration we don't have. So first we cannot use 1. R1 we cannot first use 1. Instead of it, first we have to find out the R2. So let's find out first R2. So I remove this one. So we can say R2 is equal to K, sorry, T2 is equal to CA1 minus CA0 divided by, CA1 CA1 minus CA2 divided by KCA2, capital K plus CA2. So we have tau2 is equal to 0.2 second. 0.2 second is equal to 0.2 second is equal to CA1 we don't have, but CA2 we have. It's a 1 divided by small k we have value. We have a value small k value. What is the value of small k? It's a 5. 5 multiplied by 1 divided by capital K we have. Capital K we have 9 value. 9 plus 1. So if we do this procedure, then we have 0.2 is equal to CA1 minus 1 divided by 10 multiplied by 5. So if I do the procedure, so 0.2 multiplied by 5 is equal to 10 CA1 minus 10. So 5 multiplied by 0.2. 5 multiplied by 0.2. So it's a 1 is equal to 10 CA1 minus 10. So 11 is equal to 10 CA1. So CA1 is equal to 11 divided by 10. 6 means 1.1. Let's see whether we have a same answer or not. Yes, CA1 is equal to 1.1. Now we get a CA1 value. Once using CA1 value, we can find out the value of CA0. So how we can find out it? So tau1 is equal to CA0 minus CA1 divided by small k CA1 divided by capital K plus CA1. So if I do this procedure, so K is tau1 is equal to 1. 1 is equal to CA0 that we have to find out. CA1 value we are getting 1.1. Here 5 multiplied by 1.1 divided by 9 plus 1.1. So if I do the procedure, 1 is equal to CA0 minus 1.1 multiplied by 9 plus 1.1. 9 plus 1.1. So it's a 10.1. So here 10.1 divided by 5 multiplied by 1.2. 5 multiplied by 1.1. So it's a 5.5. So 5.5 is equal to 10.1 CA0 minus 10.1 multiplied 1.1. So it's a 11.11. So 5.5 plus 11.11 is equal to 10.1 CA0. So 11.11 plus 5.5. 11.11 plus 5.5. It's a 16.61. 16.61 is equal to 10.1 CA0. So 16.61 divided by 10.1 is equal to CA0. So we have 16.61 divided by 10.1. It's a 1.644. It's a CA0 is equal to 1.64. Is there any answer is given at CA0 1.64? Yes, C will be the correct option. 1.64 will be the answer. So here it's we are. How can we say whether we are right or wrong? So CA0 is 1.64. Here CA1 is 1.1 and here is 1. So concentration is decreases. It means we are correct one. So uh, so by this way we can calculate the concentration using equation tau1 is equal to CA0 minus CA1 divided by rate equation. Anything you don't understand, just write down in chat box and let me check what are the comments from your side. Okay, 1.6 or 1.6 9999. Okay, okay. So students, this is the example of two unequal sides of CSTR in series, and this is the procedure how we can calculate this. So now to getting this graph, for example, we have minus r is equal to small k CA divided by capital K plus CA. Now what we have to do, we have to just generalize. Generally, what we have to take, we have to put K, we have capital K, we have put down the different value of concentration. So now then we can find out the rate equation. So CA constant rate equation. So once we put down the value of CA, we find out the R. So we are getting this type of graph. We have to put the CA0, we have to take tau1, we have to make slope, and then we can calculate this one. So by this way, we can also plot the graph. And once you plot the graph, by graphically, we can also do it. Graphically, or using equation, both way we can find out the different things. If they ask for conversion, so how much conversion? So conversion for tank 1. So tank 1 conversion, x1 conversion will be the 1.1, sorry, C0 minus C1. So 1.64. They are not asked, but we'll calculate for ourselves. 1.64. So 1.64 minus 1.1 divided by 1.64. It means 99.32 conversion. Sorry, it's 1.64 minus 1.1. So 0.54 divided by 1.64. Sorry, it's a 32.92 conversion. So in first reactor, 32.92 conversion. Now in the second reactor, how much conversion? It's a 1.1 minus 1 divided by 1.1. So 1.1 minus 1 divided by 1.1. So it's a 0.09. It means 9% conversion in X2. And if I take a overall conversion, then what will be there? 1.64 minus 1 divided by 1.64 overall conversion. So 1.64 minus 1 divided by 1.64. It means 39% conversion will be there after the end of the second year. 39% conversion we get it. And so we can use both conversion as well as we can also calculate conversion. We can also calculate the concentration. Any doubt up to this, you can write down in chat box. If you don't understand this concept, you can write down in chat box. So this is the example that asked in GATE example. Now what we'll do, we have take a break here. We'll break for hi. We'll have a break here. Sure, Parth. And now it's in my it's 8:38. It means we consider 8:40. We'll meet at 9 o'clock. We'll meet at 9 o'clock. Then and we'll do one theory and then we'll finish this one. And last two lectures we have a lab. We'll consider lab in last two hours. Then so now you can leave the meeting and you can rejoin the meeting at 9 o'clock. You can rejoin the meeting at 9 o'clock. Huh? So I end meeting here for all of you and we'll meet on 9 o'clock.